Hi, my name is Isaac Gerg, and I'm a PhD student in the Information Processing and Algorithms Laboratory at Penn State University in the United States. I'm under the supervision of my advisor, Dr. Vishal Monga. Today I'm presenting my work on synthetic aperture sonar image segmentation using adaptive learned beam steering. Synthetic aperture sonar, or SAS, is a coherent imaging modality which produces high-resolution imagery of the seafloor at an almost photographic-like quality. It is collected almost exclusively by a sonar mounted on an unmanned underwater vehicle. SAS image segmentation provides the ability to spatially characterize imagery, having an important role in habitat and environmental monitoring, providing context for other automated algorithms like target recognition, and dynamically modifying vehicle behavior in order to maximize survey objectives. Obtaining accurate labeled imagery for SAS image segmentation necessitates the need for divers and oceanographers to accurately characterize the imagery post-survey. This task is quite burdensome, as coordinating divers to manually survey an area is time-consuming and logistically challenging. To mitigate this, researchers generally create labeled data post-survey using human experts who are accustomed to analyzing the imagery. However, this method presents its own challenges. Disambiguation of some seafloor types requires imagery from multiple survey periods, including different sensor or seafloor orientations, since the same seafloor type may appear quite different in a SAS image, depending on the collection geometry or season. Despite the aforementioned issues with obtaining labeled SAS imagery, we were given a labeled data set, arriving at a compromise. The data are labeled post-survey by a human, but only the quote-unquote easy portions of the images are labeled, leaving the vast majority of pixels unlabeled. We refer to learning in this context as semi-supervised learning using a semi-labeled, sometimes called a weakly labeled, data set. This figure shows an example semi-labeled image from our data set. In the right image, the blue and brown areas indicate human-provided labels of two seafloor classes, while the black area represents unlabeled pixels. The border of the labeled regions is shown on the left in white. We see that the human has only labeled the easy portions of the image containing mostly unambiguous seafloor texture, leaving the remaining pixels unlabeled. For our problem, we classify the seafloor into 7 classes, with an example class highlighted in each image. The top row is the original image, and the bottom row shows the relevant class. Our classes are shadow, dark and light sand, seagrass, rock, and small and large ripple. The output of the SAS image reconstruction process is an image containing complex valued pixels. We often call this a single look complex image, and it encodes acoustic angle of arrival information. The 2D Fourier transform of this SLC, single look complex, yields a k-space representation with axes kx and ky for spatial dimensions of x and y for a long track and range dimensions respectively. Once in k-space, an interpolation can be done to arrive at f theta space, where f is the operating frequency of the sonar and theta is the look angle or angle of arrival. So for sufficiently low fractional bandwidth systems, the angular dependence on waveform arrival becomes independent of frequency. One can think of this in terms of the Fourier slice theorem, where when the ratio of the center frequency to bandwidth is large enough, the arc formed by small continuous section of look angles is locally linear. This results in lines of a constant angle to be nearly horizontal. Using this assumption, ky is now approximately proportional to theta, the look angle. With this representation, filtering in theta across all frequencies and then performing the inverse Fourier transform results in an SLC whereby the image is squinted in the direction to a range of look angles theta. This figure shows the beam geometry just described relative to the sonar array. In this work, we utilize the fact SAS imagery filtered intelligently in the k-space domain yields images with different squints or looks of the seafloor by steering the receive beam of the aperture. Sweeping over a consecutive set of look angles creates a sequence of images akin to a movie, which calls attention to aspect-dependent scattering effects and motion of objects in the receive beam during the collection. Organizing such a process is the result of domain knowledge of the SAS imaging modality, and sometimes this process is called multi-look sequence processing, or MLSP, from where our proposed network that we will show derives its name from. Furthermore, we parameterize the MLSP process so that the look angle theta naught, the beam width theta BW, and the attenuation are all learned by the network. When we filter with a fixed beam width over consecutive angle offsets, we arrive at a sequence of images useful for image interpretation. Despite reduced azimuth resolution from the filtering process, we are now able to discern aspect-dependent features such as those from acoustic shadows. In addition, we view the beam steering effect as a temporal filter, whereby visible changes image to image in the sequence are the result of motion from objects during the formation of the synthetic aperture. This figure shows an image squint sequence and corresponding K-space filter. The vertical axis is proportional to look angle, and the horizontal axis frequency. In the top right quadrant, denoted by the arrow above each image, we see a fuzz move vertically in the sequence and is likely biologics in the water column. The pseudo-motion effect is only visible when K-space filtering is performed, and without it could result in misclassification of seafloor type. We also provide the no filtering, also known as a static image, for reference. A differentiable filter function must be specified in the K-space domain in order to deploy learnable parameters for its specification. We accomplish this by employing a rectangle function as defined by the limit of a rational function shown in the equation. Consequently, defining the rectangle function as a soft approximation using a fixed n that's much less than infinity, this yields a smooth function alleviating Gibbs artifacts normally present when using a hard rectangular filter. Furthermore, we specify the relevant filter parameters of bandwidth, offset, and attenuation, all in a differentiable manner, as given by the equation of our now called soft filter function that is used in our network. Our proposed network, called Multi-Look Sequence Processing Net, or MLSP net, for SAS segmentation is composed of two primary paths, the multi-look sequence and the static image paths. The multi-look sequence path is composed of 8 filter nets operating in K-space and are initialized using domain knowledge so a useful multi-look sequence emerges. The 8 looks are sent through a shared UNet encoder, reweighted by squeeze and excitation modules, and then fed to a bidirectional 2D convolutional LSTM to extract meaningful features from this image sequence. The static image path simply ingests the input image and processes it through the UNet. Features from both paths are then concatenated in the feature dimension and processed by a segmentation network for final image segmentation. Imagery used to evaluate our experiment is from a high-frequency SAS aboard an unmanned underwater vehicle. Each image starts out as size 1001 by 1001 pixels and is downsampled using integration to 512 by 512 pixels for training and evaluation due to memory constraints of the compute we used. The dataset totals 113 single-look complex SAS images composed of 7 labeled classes and 1 unlabeled class. No location information or other metadata about the SAS system was provided for the images. The size of the training and test sets are 80 and 33 images respectively. Of the training data, we use 64 images for training and 16 images for validation. The distribution of labels is class imbalanced, and we show this in the figure. We trained the MLSP net for 500 epochs using the ATOM algorithm with a learning rate of 10 to the minus 3 and a mini batch of 64. The training iteration giving the best validation result is used to evaluate the test set. The loss function used to train the network is the weighted categorical focal loss. We evaluate and compare methods using the mean pixel accuracy, or MPA, because of its robustness to class imbalance, which is present in our data set, as shown here in the figure. To demonstrate the necessity of the angle of arrival filters in MLSP, we train MLSPNet without this processing step and report results. This is accomplished by nulling the filtering operation in each filter net so that no filtering occurs and all images fed to the convolutional LSTM2D module are exactly the same, thus removing any notion of a temporal sequence. We refer to this configuration as MLSPNet no filter in the results shown. The table shown here shows pixel average per class and the mean pixel average for several comparison methods, as well as MLSPNet and MLSPNet no filter. We see in the table that MLSPNet has the highest MPA of all methods and provides best classification for classes light sand, rock, small ripple, and large ripple. Additionally, we see superior performance over MLSPNet no filter for the shadow class, which is especially easy to confuse with dark sand, and this demonstrates the benefit of activating the learnable filter nets. This figure shows the results on 10 runs of MLSPNet and MLSPNet no filter with a random training/validation split. The figure shows MLSPNet has better performance on average for the majority of classes, but also shows reduced variance, demonstrating its robustness to training sample selection. In conclusion, our results demonstrate 1. Improvements in image segmentation performance by exploiting the complex valued nature of the SAS SLC. 2. That a network design by which phase information is handled using traditional signal processing techniques in a differentiable manner. And 3. Reduced algorithm complexity by enabling end-to-end training, thus forgoing the need to pre-process the SLC into different squints and magnitude imagery prior to network input. We hope this work motivates researchers to consider the complex valued SAS image as input to deep learning algorithms in the future. Traditionally, phase information such as this has been discarded as the vast majority of SAS machine learning algorithms focus their efforts exclusively on magnitude imagery. We also thank the NSWC Panama City Division for providing the data used in this experiment. Thank you for your time, and I will now take any questions.